Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the memory paradox. In this page, we will cover how we built the most powerful minds in history and forgot to give them a past. Artificial intelligence today is capable of feats that were considered science fiction just a decade ago. We have machines that can generate art, write code, and diagnose diseases with incredible accuracy. However, there is a fundamental structural flaw in their design. They are minds without a history. This presentation explores the paradox of building the most intelligent entities on the planet while failing to provide them with a way to remember their own lives. We will examine how this lack of a past prevents true wisdom and what researchers are doing to fix it. We are moving from static models to dynamic learners. This journey will take us through the biology of the brain and the complex mathematics of neural networks to understand why memory is the missing piece of the puzzle. We are on the verge of a breakthrough that could change how machines learn forever. The machine wakes up empty every single day. To understand what this means for an artificial intelligence, we can look at a human medical condition called Anterograde amnesia. Patients with this condition are stuck in the present moment. They can engage in deep philosophical debates and solve complex math problems with ease because their working memory is intact. However, the moment the conversation ends, the memory of that interaction is completely gone. To them, every single meeting is the first meeting. Modern large language models suffer from this exact same condition. They are brilliant in the moment and can process vast amounts of information to give you the perfect answer. Yet, they are structurally incapable of accumulating wisdom over time. Every time you start a new session, the machine has no memory of who you are or what you discussed before. It is a brilliant mind that is constantly reset to zero, preventing it from ever growing into its full potential or learning from its own mistakes. This structural amnesia is the core of our problem. Learning a new skill ruthlessly destroys the old ones in current digital architectures. This is a phenomenon known as catastrophic forgetting. It was first documented by McCloskey and Cohen in 1989. Let us look at a practical example to illustrate this point. Imagine we have a neural network that has been trained to be an expert in the Italian language. It knows the grammar, the vocabulary, and the nuances. Now, we want to teach that same network Mandarin. In a human brain, learning a new language might cause some temporary confusion, but we would not lose our Italian entirely. However, for a standard neural network, the process of learning Mandarin does not just add to the existing knowledge. It entirely overwrites it. The mathematical structures that represented Italian are destroyed to make room for Mandarin. This means the artificial intelligence cannot be a lifelong learner in the same way we are. It is forced to choose between its old expertise and its new lessons, creating a binary state of knowledge that prevents the accumulation of multifaceted wisdom. The terrain of the digital brain constantly shifts as the model learns. We can visualize this process as a literal physical landscape. Imagine a mountain where the peak represents the optimal solution for task A through a mathematical process called gradient descent. The artificial intelligence climbs this mountain to find the best way to perform that task. However, when the system is asked to learn task B, the entire terrain shifts. To reach the peak of the new task, the optimization process must adjust the billions of weights inside the model. Here is the problem. Knowledge in an artificial intelligence is not stored in isolated files or folders. Instead, it is a distributed representation, smeared across billions of interconnected weights. This is known as the manifold shift. Because the optimization process does not know which weights were critical for task A, the mathematical foundation of the past is bulldozed to make room for the present. It is like rebuilding the entire world every time you want to learn something new, leaving no trace of what was built before. We currently avoid the problem of forgetting by freezing models in time. Imagine an artificial intelligence as a piece of high-tech hardware encased in amber. Once a model finishes its initial training phase, it is mathematically frozen before it is deployed to users. This is done to prevent the model from destroying its own mind during everyday interactions. However, this safety measure comes with a significant cost known as temporal drift. For example, a medical artificial intelligence that was trained in 2022 genuinely cannot know about medical treatments or breakthroughs that were discovered in 2023. It is a snapshot of the world at a specific moment in time. The only way to update the world of the model is through a profoundly expensive retraining cycle. This is effectively a complete memory transplant. We have to discard the old brain and build a new one from scratch using all the old and new data together. This makes our current systems static and incredibly expensive, rather than fluid and adaptable like a living mind. There is a fundamental mathematical tug-of-war that every artificial intelligence developer must face. It is the balance between plasticity and stability. Plasticity is the ability of a system to be flexible, absorb new data, and rewrite its internal connections. On the other side, stability is the ability to lock in information, preserve structure, and protect accumulated knowledge. This dilemma is governed by a concept called the continual learning effective model capacity. The mathematical reality is that maximizing one of these traits inherently destroys the other. You cannot simultaneously be perfectly rigid and perfectly fluid. If a model is too plastic, it will forget its foundations immediately. If it is too stable, it can never learn a new skill. Finding the balance between these two opposing forces is the greatest challenge in creating a machine that can actually mature over time. We need systems that can hold on to the past while embracing the future without one side winning the war and destroying the utility of the model. The human brain solves this problem by using a two-stream architecture. This is described by the complementary learning systems theory. The brain avoids digital dementia by splitting the workload between two distinct areas that work together. First, we have the fast learner, which is the hippocampus. It is highly plastic and uses sparse representations to rapidly capture the episodic events of the day. Crucially, it does this without overwriting old memories. Then, we have the slow learner, which is the neocortex. The neocortex is highly stable and extracts statistical regularities slowly over time to build permanent semantic knowledge. By separating immediate experiences from long-term structural knowledge, we can learn a new piece of trivia today without forgetting our childhood home. This biological blueprint is what artificial intelligence researchers are trying to replicate in digital form. We want to create models that have both a high-speed recording system and a stable long-term library of knowledge that can grow without interference between the two different learning systems. We practice the past while sleeping to protect it from the future. This is a vital biological function that machines do not yet possess. During slow wave sleep, the hippocampus replays compressed versions of the day experiences in a process called memory replay. Through specialized neural signals known as thalamocortical spindles, the fast learner systematically teaches the slow learner. The neocortex only learns new information when it is actively mixed with reminders of the old. This is known as interleaved rehearsal. Essentially, the brain requires an offline night school to preserve its history and integrate new lessons into the existing framework of knowledge. This prevents new data from simply washing away the old. For an artificial intelligence to truly learn and retain information like a human, it may need its own version of a sleep cycle where it can reorganize, prioritize, and reinforce the lessons it has learned during its active periods. This offline processing is the secret to human wisdom and stability over many decades of life. Engineering a digital long-term memory requires three primary strategies to overcome the limitations of standard neural networks. The first strategy is regularization. This involves protecting the essential connections that have already been formed by making them more resistant to change. The second strategy is replay. This is like the machine dreaming of the past. By mixing old data with new data during the training process, the model avoids overwriting its previous patterns. The third strategy is expansion. This involves growing new neural real estate. Instead of trying to fit every new task into the same fixed number of parameters, we allow the network to add new layers or nodes when it encounters a completely new type of information. By combining these three approaches, we move away from static systems and toward entities that can grow in complexity and knowledge without sacrificing the expertise they have already worked so hard to acquire. This framework allows for a model that behaves more like a living organism that evolves with its environment. One of the most effective ways to make the past stiff and resistant to change is a technique called elastic weight consolidation. Introduced by researchers at DeepMind in 2017, this method mathematically identifies which weights in a network are load-bearing for old tasks. It uses a metric called Fisher information to score how sensitive the performance is to a specific weight. High Fisher weights become like stiff springs that resist change during the learning of new tasks. This is known as the quadratic penalty. Meanwhile, low Fisher weights remain fluid and flexible, allowing the network to learn a new task without breaking the old architecture. It is a beautiful mathematical solution that mimics how a building is reinforced. We strengthen the core pillars that hold up the structure while allowing the non-essential parts to be modified. This allows for a level of stability that was once thought to be impossible in traditional neural networks, enabling the model to learn sequentially without losing its previous foundational training. To avoid privacy nightmares, an artificial intelligence can dream of its past using synthetic data. This is an important consideration because it is often illegal or impractical to store all past user data, such as private medical records, for later rehearsal. To solve this, we use a technique called pseudo-rehearsal. Instead of storing actual data, a secondary teacher model generates statistically accurate synthetic memories of past tasks. Then, advanced systems use progressive latent replay to replay the compressed features of those past tasks. This operates very similarly to human episodic reconstruction. We do not remember every single detail of a memory. Instead, we reconstruct the essence of it based on patterns. By training on these synthetic dreams, the Scholar model can maintain its old skills and knowledge without needing to keep a massive database of sensitive original data. This protects privacy while allowing for the accumulation of experience and the prevention of forgetting. It is a way to maintain history while respecting the boundaries of data security. Another approach to solving the memory paradox is to build a network that never overwrites, but only expands. This provides a state of absolute stability. Progressive neural networks, developed by DeepMind in 2016, completely freeze older task columns. This makes them structurally immune to the threat of forgetting. When a new task arrives, the system is given an entirely new, freshly initialized neural lobe to handle it. The catch here is that memory and compute costs scale linearly with every new task. If you learn 1,000 tasks, you need 1,000 times more memory. To make this sustainable in the real world, systems now use dynamically expandable networks. These networks are designed to grow only when it is absolutely mathematically necessary. They seek to use existing knowledge whenever possible and only build new structures when the task is truly novel. This allows for full plasticity for new knowledge, while guaranteeing the past is preserved without breaking the bank on hardware costs and memory requirements. True intelligence is an accumulation of experience over time, not just a static snapshot of data. When we look at a human expert, their brilliance is the result of 30 years of integrated, lived experience. It is the product of thousands of failures, successes, and adjustments. It is not something that can be captured in a single static exam. In contrast, current artificial intelligence has no history. It only has a training run. Without an accumulated residue of learning and failure across time, a machine is categorically barred from reaching true intelligence. We can see this in the difference between a modern computer chip and a geological core sample. The chip is a fixed snapshot, while the core sample is a record of time, with each layer representing a different period of history. Until we can build systems that function like that core sample, where every interaction leaves a meaningful and lasting layer, we will only have sophisticated calculators. True wisdom requires the passage of time and the integration of many different lived experiences. Identity itself requires a continuous thread of memory to exist. Famous cognitive scientists like Daniel Dennett and Antonio Damasio posit that identity is essentially a story the brain tells itself about its own continuity through time. This is known as the narrative self. Currently, artificial intelligence lacks this vital narrative arc. It cannot understand the present moment as a part of a continuing story. Instead, it treats every single interaction as if it were a first meeting, disconnected from everything that came before. This has profound consequences for areas like continuity of care in medicine. A medical artificial intelligence cannot be a genuine partner to a human until it can remember past interactions and understand the context of a long-term relationship. Without a memory of the past, there is no sense of self, and without a self, there is no way for a machine to truly understand the complex, social world of humans. Memory is the glue that binds a character and a personality together over time. Finally, we must give the machine a forever. We have spent decades building systems that are capable of answering almost any question we can think of, but we have not yet built a system that is capable of wondering. Wondering requires a deep context of what is already known and an understanding of the gaps in that knowledge. Genuinely earned intelligence is defined by the unique process by which a mind came to know the world. Every step we take toward the goal of continual learning is a step toward a machine that grows wiser with time rather than just more data-heavy. We are moving from the era of answering to the era of genuine exploration. We are building the foundations of a digital past so that these systems can have a meaningful future. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.